Next talk will be Considerations of Radiative Transfer by Bill Sharp.
Okay. This is a result of a seed of thought put in my mind by Charlie when I was a grad student. I had the fortunate circumstance of coming to Colorado in '66 with a number of others here on a NASA fellowship. So that meant I didn't have to go be a research assistant for some person I didn't care for or didn't want to do or whatnot. I could sit at my desk, do my studies, and peruse the faculty to decide who it was I wanted to do my work for. And so I decided that I would take a course in the summer of 1968 from Charlie on the aurora and air glow. And in the course of that study, he was very good at presenting me the different aspects of aurora and air glow, some of the attributes of it, some of the chemistry. And I need to change these things, don't I?
Error was there.
Wrong direction.
Yeah.
That one, okay.
That's, Bill, that's illegal.
That's what?
I said, that's illegal.
Equations.
Oh, well, I'm not going to talk a lot about it. I'm just going to give you some results. The impetus was that one of the topics we talked about was radiation transport. I looked at that, and as Jim has rightly pointed out, I thought, boy, I hope I never have to deal with that. That looked like it was complicated and lots of programming and lots of great thought. And I wanted to stay in the air, do running instruments on the ground, and just get data and fiddle it with ideal programs. Anyway, for those of you who are science prone in here, there's the first part of that, which is the Beer-Lambert law, which is the absorption in the mass of the atmosphere. And the second half of that is emission being produced inside this little space of atmosphere by radiation coming in from the outside and impacting something that's in that little gas column. That's the part that's important for what I want to talk about. And the key in there is that the source function that the J sub nu describes how that process works, how that emission is created. And of course, all of you who are familiar with optical depth know that that tau on the right is the integral over the absorption coefficient. Key thing to remember about this as I go on is that stimulated emission is in phase with and in the same direction as the incident radiation that whacks the molecule or atom that it hits. And it's important in a number of different environments. 45 years later. Yep, I was contacted by some guys at Langley, NASA Langley. They were working a problem with ITT Aerospace, ITT Space Systems, which is now Axelis, which is about to become Harris. So they asked me to answer a question that they were peppered with and did not have the answer for, and it had to do with the amount of 1.27 air glow that was impacting their sensor, which was a laser absorption spectroscopy experiment on O2 in the atmosphere. They needed that in order to calculate the surface pressure to determine the mixing ratio of CO2, which they also had with another laser-based system. So I said, well, yeah, I remember 1.27 radiation. That's an air glow feature that comes from ozone or from an excited state of oxygen, and I should be able to help you get that answer. So because of SME, and the fact that they were actually trying to get ozone measurements deduced from the emission from that state, I figured there was lots of that state in the atmosphere. So I decided that I would put together a model, and on the left is this model, which is a vertical structure of the rat's nest that Scott showed earlier, but for a different bunch of molecules. But what happens here is that the in state for all of these processes where ozone is dissociated by sunlight and O2 is dissociated by sunlight, and there's even some chemistry going on, is that a lot of the energy ends up down here in O2 singlet delta, and of course it just sits around for about an hour. And it can be quenched, it can radiate, which is the 1.27, and I stuck in here a couple of lines that show where this laser experiment was going to work in trying to do the column concentration of O2 in the atmosphere. Turns out that when I did the model calculation, I got the profile you see in the right frame there. That's about the same kind of profile that they were getting from SME, but they worked backwards and did the O singlet delta, O2 singlet delta distribution of altitude. The top part is mostly the three-body recombination, and the middle part is all the rest of this stuff. And so it makes quite an impact, and it turns out that that is a significant amount of O2 singlet delta in the atmosphere compared to the neutral atmosphere. It's not an unreasonable fraction. Calculating the air glow from that, it turns out that the results that from my model agreed pretty much with what SME was getting, and some ground-based measurements that had occurred in the daytime, as well as a number of rocket flights that had flown through the layer. So that takes care of the chemistry, and I saw, yeah, I can calculate the air glow, and I can make an estimate about the impact on the laser experiment. But what about all of this O2 singlet delta that's in the atmosphere? We're using that to do the absorption experiment. I've got a powerful laser sending a beam down through the atmosphere. What's it doing when it hits that O2 singlet delta molecule? Well, it must be stimulating the emission. Well, is that significant? Is it important enough to do that? Well, you all know that's kind of the way lasers work. You keep getting amplification in your laser signal. So what I did was that, recall that right-hand equation, which was the stimulated emission part. I said, okay, I'm going to break this problem into little chunks of 1 kilometer levels. And inside that chunk, the source function is going to be constant. The absorption coefficient is going to be constant. And then I'm going to do a piecewise computation from the atmosphere from 150 kilometers down to the ground, reflect, and come back out again. If you do that, you can reduce that fancy stimulated emission integral to the one that's at the bottom there, which is something I could put on a computer and work with in some reasonable fashion. But the kicker was, as Charlie told me 45 years earlier, figure out that source function. Well, geez, I spent a year trying to figure out that source function. First time I did it, I got the wrong source function, and I got a result, and I told the guys, you've got no problem with your experiment. I went back and I said, that can't be right. This is too much O2 singlet delta. I got the wrong source function. So I went back, and this is the one that works. Actually, this is the right way, because you've got the energy in the transition, and you got Einstein's coefficient there, which is the stimulated emission coefficient, which is constant, doesn't change. And you've got the line shape, which is important because that is a function of where you happen to place your laser if you're doing absorption. And you've got the irradiance from the laser, which is E over C, terms of ergs per square centimeter per second, and I'm getting dangerous there with the science stuff. And then the fraction. Well, of course, the molecule is populated at some rotational level, which is what that frac J means. And then, of course, you've got the concentration of O2 singlet delta. So I did that calculation, and I did a couple of scenarios with the laser. One of them was that the laser was tuned at, I'll try this, maybe it works. Was tuned at, well, I guess it doesn't work. Was tuned at the trough between two strong lines here. And then there was another laser tuned off frequency where you would expect to get no absorption. And then I tried one with a laser right on the center of an absorption feature, and again with a beam just off. And I did those series of calculations, ran the beam down to the atmosphere and back out. And the question that I asked myself was that if it gets all the way down, it comes back out, and I've got the same radiation coming back to the telescope as I would expect for no stimulated emission, and I was fancy free, I could tell the guys no problem. Well, guess what? Answer is, my function was a little wild, but it was correct in the end, because if you look in that 32-degree north, in the solar zenith thing, we'll call them 10, which means you basically have an overhead sun in the summertime. 32 degrees north, for the laser return irradiance coming back to the telescope. You had 1.8 times 10 to the minus 13 irradiance units. At 90, if you had not even treated stimulated emission, you would have 1.4. There's more radiation coming back up through the atmosphere as a consequence of the presence of O2 singlet delta in the atmosphere than there would be if there was not. That was for the trough region. The next to the bottom line there, ratio air glow to the 08 to the online laser frequency. You can see that number is bigger than unity, which means there's lots of air glow radiation impacting, which is stronger than the laser signal coming back. And of course, in the bottom one, which is solar upwelling radiation on the telescope, that's hundreds of times stronger than the radiation that's coming back from the laser. So you think this is a dead experiment, it's not going to work anywhere. First of all, it's not going to work in the daytime because you've got more radiation coming back than you expect to get back, even than you're sending out. So the result of all that was that the air glow and the solar radiation are slowly varying compared to the laser, which is a BN-coded CW laser. And it's oscillating in the kilohertz range. If you do some phase-sensitive detection, you can get rid of the constant background. Now, you're going to have some error problems because the error is not going to go away, but the absolute intensity is going to not be a problem for you. But the hooker is the stimulated emission is going to kill you in the daytime. You can't say anything about your absorption measurement in the daytime or when the sun's at 90 degrees. In the nighttime, it works because the O2 sigma delta has slowly decayed away in the course of the night because of its lifetime. And the laser is going to give you the correct kind of absorption. So if it works in the nighttime, it won't work in the daytime. That's what I told the guys. They were unhappy about it. But that's what the science tells you, buddy. That's the way it goes. That's it.
Question? Chairman?
There's been some question about what the A coefficient is for the sigma delta transition.
I forgot.
I mean, there was a number that was used all the time, and that's been
Yeah, I know it's been twiddled around, and it's whatever the current community believes is the right one.
So did I see 10 to the 11 O2 sigma delta? Or was that the first model? Because that's all.
No. I don't think that was 10 to 11.
It was probably a model, that's why you don't want to go back.
You did.
No, it's small.
10 to the 11?
Oh, but that's up at 50 kilometers. There's still lots of O2 up there.
No, but that's more than a part per million.
That's right. There's a lot of it up there.
So what are the chemical manifestations of that much O2 sigma delta?
Well, that's how the guys measure ozone.
I know, but what about the interaction with the other reactive systems? That's a remarkable amount.
Yeah.
It's not very energetic.
I know, but it's still very close.
Yeah, Scott's program showed the consequence of some of that stuff going on in the chemistry to get into the NO cycle stuff. Yeah, I was amazed when I looked at the SME converted their air glow measurements to the column concentrations and lots of it. Okay.
We'll go ahead and keep moving, but
Sure.
thank you for that.